Hello, everyone. My name is David Talby, and what I'd like to talk to you today is about natural language processing, specifically in healthcare for medical and clinical record, which is something we've been working on for a while, and I want to show you how you can get state-of-the-art results in exactly one line of code in your project today. The reason I'm here giving this talk is because we've been fortunate at Johnson Labs to do a lot of work in very different areas of healthcare, life science, biotech. We are the team behind the Spark NLP library, which for the past 4 years has been the most widely used NLP library in the enterprise. And specifically within healthcare, that has always been our main area of focus. We're almost 60% of the market. So we work with the majority of the world's largest pharmaceutical companies, large healthcare providers, healthcare centers, and several dozen software companies who are building solutions that need to understand medical text. If you're not familiar with the healthcare space, here are a couple of examples to show, just to give a hint of the kind of language we are dealing with. So this example is from a public case study of work we've done with Kaiser Permanente. Kaiser Permanente is a US healthcare system that serves over 20 million patients in the US West Coast. And what they wanted to do was they wanted to be able to predict within a hospital how many open beds am I going to have in the next shift, next 2 shifts, and how many nurses of which type I need in the hospital. And one of the challenges is in doing that is understanding the people in the emergency room, because in the emergency room, you have fairly little structured data about the person. You have the basic, age, gender, whether they're insured, but not, not labs, no prescriptions, nothing coded. And you have these triage notes that the doctors and nurses write. And if you could read them, you can see, for example, since yesterday, 10/10, Tylenol, constant Tylenol 1 hour ago, plus nausea, diaphoretic, mid-ABD radiates to back. And as you can see, all of these sentences, they are not valid English sentences. They have their own kind of shorthand and grammatical structure. So 10/10 is level of pain. Constant Tylenol is what the patient took at home. Since yesterday, it's kind of when did something start. Mid-ABD radiates to back. The abdominal, so stomach pain radiates to the back. It's always a mix of things. And you want to be able to understand these kind of text that's obviously very, very, very specific to healthcare, very specific to a specific context, and be able to extract structured features. What hurts? When did it start? What did you take at home? Where does it hurt, right? So that you can then build downstream machine learning models, and in this case, predict admissions, right? Predict length of stay, and so on. So that's our goal. Our goal is to understand those very, very specific clinical contexts. Here you have, once it clicks, here you have another example on the left. This is also from public case study of work we've done with Roche, the pharmaceutical company. Roche has built a software platform for clinical decision support focused primarily on oncology. And one of the things you have to do in oncology, you have to be able to parse and understand pathology reports, radiology reports, genomic sequencing reports, and lab reports in order to understand really what kind of cancer a person has. And first of all, as you can see, this requires OCR as well. You get scanned reports, you get visual images, you get handwritten notes on one hand. On the other hand, what you need to extract is also not off the shelf. So you don't need to extract the person's symptoms or diagnosis or what drugs they're taking. You need, in this case, you care about 2 more characteristics, so 2 more staging, histology, TNM value, grade, margins, laterality, primary versus secondary tumors. So things that are specific to a specialty in medicine. So a lot of the work is really working with doctors, understand clinically what is necessary and relevant, and then learning to extract and structure it correctly from those terms. So those are the kind of challenges and the kind of projects we deal with in the healthcare space. And to do this and to be able to both get you the state-of-the-art accuracy and do it in one line of code, there are 3 tools that you have at your possession. One of them is Spark NLP for healthcare. And so that is a software library that implements the state-of-the-art models for clinical and biomedical NLP. And we will talk about some of the tasks it has. but it's a software library. There are Python APIs, Java APIs, Scala APIs, as well as a set of pre-trained models. So I now more than 700 models for different specific different NLP tasks that are supported. So that's one tool that you have. The second tool in your tool belt is Spark OCR, and that is another software library that extends those capabilities to visual documents. And it started as an OCR library. So if you had a scanned PDF, right, or an image, or of a report, you first convert it into text, and then you run your text analysis and NLP pipelines on top of it. In the past 2-3 years, the model has changed, and now really what we support are end-to-end deep learning models that combine computer vision and NLP aspects. So that really what you do, you analyze the image as an image and extract the facts that you care about in a structured way. And this increases accuracy because, as you know, as humans, when we read forms, sometimes, yes, we read the text and the words. So, oh, this lab result, okay, here's the value. But sometimes we look at things visually. So you say, oh, when is the patient's name? Oh, it's in the big font on the top left. Where is the date? It's in the top right, and it is a certain format. So really what you want to be able to use both computer vision and text together, and some of the newer language models, language embeddings enable you to do that, and that is what we have implemented here. The third interesting tool that you have in your disposal to really get it down to one line of code is the NLU library. And this is a free and open source Python library, which exposes more than 5,000 different pre-trained models, as the name says, with one line of code. So the goal here is to be open source, to focus on this one line design principle, and to very easily scale and integrate with the rest of the Python ecosystem. So for example, you can, as you see, you can analyze the text within one line, but you can also send a pandas data frame, you can send a Spark data frame, you can send a Ray data frame, and really within the same one line of code with no changes, you can scale to a cluster, leverage GPUs, and so forth. So here are some examples of how this code actually looks like, and everything you see on this slide is free and open source. So we'll start from the left. If you want to recognize named entities, you can do nlu.load, ner.predict. Angela Merkel is from Germany. And what load does, it loads whatever models are necessary, in this case for name entity recognition, hence NER. So it loads the embeddings, it loads the pipeline, it loads the tokenizers, it loads everything you need into memory. And then you call predict on a text, and you get back the data frame that you expect to get. Just that in this case, Angela Merkel is a person and Germany is location. You can also do text classification. So if you ask it nlu.load, en.classify.fake news, so in English classify for fake news, Unicode cited on Mars, it tells you that unfortunately they haven't yet. And on the right, you can see additional examples, grammar correction, changing the style of text, right, from formal to informal, from active to passive. You can do question answering, you can do language translation, you can do spell checking, you can do emotion and sentiment analysis, you can do general question answering, and really several thousand models that are available to use that. But now let's focus on what's available here specifically for the healthcare space with the Spark NLP for Healthcare library. So the first task that you need whenever you're analyzing this kind of text is named entity recognition, which, as the name suggests, asks the software to read the text and tell you entities that it can find, and this is very, very context specific. So you can see on the top example, you have an example from a radiology report. And when you're reading a radiology report, so for example, when someone had an X-ray or a CT scan or an MRI, you care about things like, what was the test, what was the body part, what is the directionality, right? We look at the lower lobe or upper lobe of the lung. What were the findings, right? Do we see any black mass, right? Do we see anything that's unusual or interesting? And those are the things you care to extract, right? So that you can see, oh, is this patient at risk? Is this patient a fit for this clinical trial? What is the best next action for this patient? Right? Which doctor should we recommend or match them with? So that's just one example, radiology. Here at the bottom, you see another example, this time looking at medications. So in extracting medication, you don't just care about the name of the medication, you want to know the dosage, the frequency, the route, the strength, and sometimes also whether it's planned or not, right? But in general, you need to see really what was prescribed in a very structured way, right? Because if your questions, for example, how much OxyContin did the person take in the last 7 days, right? You need to understand the dosage, how many times per day they're taking it, and when are they taking it? How are, is it like by mouth or by IV? And all of that is available and structured to you as well. So overall, there are more than 400 types of entities that Spark and NLP for Healthcare can extract for you just right out of the box with pre-trained models. So there are some additional examples here. On the top, you can see a medical risk factor. So this is very popular if you're really just trying to analyze a large body of patients and find people who are at risk for different things. Undiagnosed diabetes, undiagnosed depression, pregnancy that's at risk, evolving kidney disease, and so on. So some of the features you want are kind of the classics: hypertension, hyperlipidemia, obesity, diabetes, smoking, alcohol abuse, and so on. And at the bottom, you see another super popular example for de-identification. De-identification is a use case by itself, so just being able to take free text, medical text, and automatically de-identify it, so anonymize it. Starts with being able to find names of patients, names of doctors, names of hospitals, dates, addresses, and professions, and so on within medical text, and then being able to replace or obfuscate them in the correct way. So those are so name and recognition is the first task you would usually want to look at, right? If you're looking at question answering, right, at summarization, at any downstream clinical decision support. And as you saw in the example, you have the one line of code there for each of those 4 examples we saw. But the other important thing is really how good is this? And when we say that accuracy is at the state of the art, it's not a marketing term, it has an academic meaning. And the academic meaning is that there are peer-reviewed papers that showing that these specific implementation, these algorithms, have the best accuracy ever achieved on a set of competitive benchmarks. Competitive meaning not benchmarks that that my team has created, but benchmarks that are widely studied, that are 20, 30, 50 other research teams that have competed and tried different algorithms on the same public benchmark. So that when you show results, right, you actually show results with those. There's a significant baseline on current deep learning, transfer learning algorithms that you can test yourself against and really see, okay, are you, is this for real? The code has to be public, the paper has to be public, and again, it has to be peer reviewed by others, right? So you cannot just write whatever you want. And for us, in addition to those academic criteria of what the state of the art usually mean in academia, we also require that the code is actually deployed in production in multiple places. Why multiple places? Because as you know, if you've done machine learning, it's very easy to customize a model for one customer, one project, one data set, one use case. What we wanted here is we wanted to build a library that can apply across healthcare. So for us, a model is kind of, we call it, ready and done when it's actually in production and in use on real world data, kind of, messy real data in multiple places. So that's our criterion. And for example, for clinical name recognition, we've been publishing papers for a few years now. There's a recent July 2022 paper that has shown these results on 3 very, very popular benchmarks in the clinical NLP space. So clinical concept extraction, so extracting diseases, diagnosis, problems, symptoms, de-identification, the 2014 Entosito, and 2018 Entosito medication extraction. And here are the F1 scores, and you can look at kind of the last basis, what we found so far as other papers competing on the same benchmarks. We've also published also with code so that you can run and reproduce it yourself, benchmarks versus AWS, Azure, and Google Cloud, and shown that these models actually make 4 to 6 times fewer errors than what those public cloud APIs produce, the healthcare specific NLP APIs. And of course, the code is public. You're welcome to look it, download it, try it yourself. Another kind of text that you deal with a lot in the healthcare space is not clinical text, meaning not a patient record, right? So I went to the patient and there's a description of me and what happened to me, but biomedical text, meaning academic research papers, clinical trial results, grants, clinical trial protocols, and other documents that basically kind of talk about medical knowledge in general. And you can see here two examples on really biomedical name and recognition. Both of them, in this case, are in the genomic space. But what's very popular nowadays is to be able to automatically read medical papers and, for example, build knowledge graphs, answer questions, right? To understand, okay, which genomic variants or gene expressions are relevant to these diseases or those phenotypes, which drugs or types of activations are most likely to work, where should we try drug development, drug repurposing, by basically trying to automatically read and summarize this kind of academic research. So quite a few of the models we have help you do that, and if you go to the website, you'll see there are quite a few kind of public technical talks and case studies on how that's been done, and that's been used kind of in the wild. Within biomedical name and recognition, also there's a paper, it's now 18 months old, that shows that on 8 out of 8 of the most kind of really the most widely used studies benchmark for biomedical NLP, in 7 of them you're actually able to achieve new state-of-the-art accuracy with the deep learning algorithms, models, templates, embeddings that are currently implemented. Once you've done with name entity recognition, usually that's still not enough to answer questions. The next thing you'd want, and that's a separate deep learning problem, is assertion status detection, which basically asks the following question: okay, fine, you found that, for example, cancer is a problem or diagnosis, good for you. What are you asserting about it? So if you read this example, right, so here we have patient diagnosed with cancer in 1999. Okay, so the patient has the diagnosis, it's present, it's positive, versus no sign of cancer was shown by the scan. So here we have the entity cancer, but it's negative. Right? It's actually important to extract it, but say, oh, we negated it, right? It's clinically important, but as a negative finding. You could also have things that are kind of maybe. So tests indicate patient might have cancer. So that's a possible on that cancer. Another important thing is to tell between the future and the past. So CT scan is scheduled for 23, so that's planned, that's in the future, versus the patient's leg was amputated last year. That's in the past, right? So being able to tell whether a patient has something today versus they had something 15 years ago is obviously clinically important. And the last thing that's critical is be able to differentiate between the patient and someone else. So if the patient's father has cancer, that is relevant, especially if you're dealing with cancer, but it's not about the patient, right? This is family history. So you want to extract the cancer entity, but then to recognize the assertion status is family, is someone else. Okay, so this is what assertion status detection does. It tells you whether something is positive, negative, speculative, whether it's future, present, or past, or whether it's about, for example, the patient or family member or someone else. And this is, of course, essential to any downstream patient cohort building, search, question answering, decision support system you'd like to build. Within assertion status detection, one of the most popular metric is from the 2014 and to CITO, and here also we were able to show in a paper last year achieving a new state-of-the-art accuracy for this kind of task on this public benchmark, with also peer-reviewed paper on public code, using basically a combination of really healthcare specific and healthcare tuned current deep learning techniques. If you're interested in the detail, there is a paper. The paper does describe the neural network architecture, the pre-processing, and basically how that was done. The third task I want to talk about, which is usually also critical in kind of the NLP pipeline and the set of tasks you have to understand any medical content, whether clinical or biomedical, is finding relationships between entities. And you can see some examples here. At the top, patient reported numbness in left hand. So numbness is a symptom, that's great. Hand is a body part, left is a direction, but of course you need to tie them together, because the next sentence says also reported pain in the shoulder. of course, you need to extract the relationships, not just the entities, to know that the numbness was in the hand and the pain was in the shoulder. Right? If I just give you the list of words, yeah, I mean, just not useful by itself. There are over 50 types of relations that Spark NLP for Valga can recognize out of the box. And then just like NER, just like assertion status, these models are also trainable. So if you're dealing with a specialty or kind of text or a language where there is no pre-trained model for, you can fairly easily tune or train your own. So some of the extracted relations, as you see, look for connections between body parts and procedures, body parts and symptoms. Temporal relations are very popular. You can see in the examples below, so understanding when something happened exactly. Did something happen before or after something else? Is something that's critically important for clinical decision-making, clinical decision support, real-world evidence, any deduction from these kind of texts. It is also important to understand that what you can do with relation extraction is not just tied to things, but also you can train models to understand what kind of relationship you're semantically describing. So for example, here we have, look at the above sentence, so we have infection resolved with antibiotic course. So this is a case where the medication, the antibiotic solved the problem, versus the tumor was growing despite the drain. So this is the case where you did the treatment, right? You drained it, but the problem actually persisted. So as you can see here, the model can actually find out the relationship, right, between the treatment and the symptom. But also understand that this is a different kind of relationship, right? So sometimes you take a medication, it helps with disease. Sometimes you take a medication, it still grows. Sometimes the medication causes a symptom, right, as a side effect. There are 6 or 7 types of semantic relationships between really just symptoms and treatments. And you need the trained models that tell you what the situation is really. The example below is not from clinical text, but from biomedical text. When you are reading medical research, for example, you want to extract, in this case, a relationship between drugs, right? So is there a drug-drug effect between them? One important thing, for example, is to know whether the sentence tells you that there is or isn't a drug-drug interaction, right? So you can see in the example here, the first sentence tells you that there is a kind of a mechanism that causes drug-drug interaction. But in the second sentence, there just isn't. And you can see the relation type here is DDI false. So drug-drug interaction is false in the second case. Okay, and this is also important, for example, if you're trying to understand if this protein is a activator or inhibitor or does not impact, right, another biological mechanism. What you want to extract is structured data, right? If you're building tables, knowledge graph, question answering, whatever may be the case, you have to be able to semantically understand the text and extract the relationship correctly, which current NLP models can do fairly well. And this is another example. Also, we have a recent paper from this year that shows that really some of the most widely studied and widely kind of highly competitive relation extraction benchmarks. So relation extraction between symptoms and treatments, like the example shown here, a temporal relation extraction, right? So what happened before what, and also an important one practically is extracting adverse events. So basically bad side effects that happened to you when you took a drug. We were able to show on 7 of those related benchmarks new state-of-the-art accuracy. So also the models that they're not perfect, but I would say that the models we have built now, which the paper describes in more detail, are really kind of the most accurate that were kind of publicly tested and peer-reviewed, and those are available to you out of the box. So in terms of how you solve problems, what these kind of tools provide you, and as you saw with one line of code, they provide you the building blocks. What you can do, you can build pipelines. Okay, so you can say, okay, I have this large body of text, I need to scale it, which it's called Spark NLP. It can scale to a cluster, and then you can come and say, I want to run these 3 NER models, these 3 relation extraction models, these assertion status, and put them together to build a solution. If you're looking to learn more about the solutions in a free way, so one thing on the NLP Summit website, there are right now really more than 200 videos of technical talks of people really from the industry talking about how they applied NLP solutions kind of in the real world, lessons learned, best practices and which libraries were used from across the industry. And also, if you go to the Spark NLP in Action website, there are more than 300 live demos and Python notebooks that you can look. You have to see the code, try it yourself, and also the notebooks are collab notebooks, so you can actually just run them within your own Google account, change the text, and see what you get. And with that, I would like to thank you for the time. I wish you the best of luck and success in your project. I mean, we all have the responsibility to help advance healthcare together. And please feel free to contact me, if you have any questions or anything we may be able to help you with, so that we can all make some progress together. Thank you.